All right, so we're going to talk today. Let's get started. We're going to talk today about a couple of tests for convergence of series. So we don't always want to have to look at the sequence of partial sums to decide if a series converges. So we're gonna develop some other tools. But first, I want to do an example. We know that, or we've been told that repeating decimals are rational numbers. And rational numbers means they can be written as a ratio of integers. So let's express. Well, that's kind of. We want to express 5.23 repeating as the ratio of integers. So this is a rational number. Rational numbers can be written as a ratio of integers. So let's take a rational number and write it as a ratio of integers. Any ideas what we would do?
Well, because you can get rid of the 5 and just put that out front, so you're really only
5 plus, okay. And I'm going to write 0.23 repeating as 0.23 plus 0.0023 plus 0.000023 plus dot dot dot. Well, now I'm going to write this, since we're talking about ratios of integers, 5 plus 0.23, 23 100ths. 0.0023, 23 over 100 squared, plus 23 over 100 to the third, plus dot dot dot. Well, what is this? That's a series, and it's geometric. So I'm going to write this as 5 plus, I'm going to factor out the 1 of the 23 100ths, because I want to start with 1. We want our first term, our n, to be 0 for a geometric series, plus 1 100th, plus 1 over 100 squared, plus dot dot dot. And this is 5 plus 23 over 100 times the sum, n equals 0 to infinity, of 1 over 100 to the n. And then we can say this is 5 plus, we can find the sum of that thing, because this is a nice geometric series, 1 over 1 minus 1 100th, which is 5 plus 23 100ths times, this turns into 100 over 99. And I can write this as 518 99ths. Or 5 plus 23. So 0.23 repeating is 23 99ths. We can use a similar process to show that 0.999 repeating equals 1. So any real number has 2 expressions. We could write 1.3 as 1.2999 repeating. So we can come up with 2 equivalent expressions for any number using this kind of process.
Why would you ever want to do that, or is it just that you can?
Just that we can.
Could you also write it as like 1 is 1.000 What's the series for what's it like 0.0001 over?
I don't think so.
Why,
No.
why not? Either way, it's like the same way.
Well, it has to do with does that expression converge to 1? So 0.9999 repeating converges to 1. The other one I don't think does. All right, questions there? I love this kind of problem. All right, let me make a quick note here, and we'll talk about this more as we move forward. The convergence or divergence. So the convergence of a series, it is not affected if we delete a finite number of terms from the beginning. So for example, the sum n equals 4 to infinity of 1/2 to the n, and the sum n equals 0 to infinity of 1/2 to the n, both converge. And not only do they both converge, but we can find this sum by finding the sum of the infinite series and then subtracting off the sum of the first 4 terms to get the sum of this series. So we can delete a finite number of terms from the beginning of the series. The convergence or divergence isn't affected. I want to list out a couple of properties, some arithmetic that we can do with series that might be helpful as we do various manipulations. So I'm going to say the sum, and I'm leaving off the 0 to infinity or 1 to infinity. So these are both infinite series, and these converge. And C is a real number. If we multiply each term, and I'm going to leave off the 1 to infinity. If we multiply each term by a constant, this just multiplies the sum by a constant. So you can factor out a constant term. And that's what we did in the example. We had a 23 over 100 that was common to each term. We just factored that out. We can add or subtract. So the sum of a sub n plus or minus b sub n equals a plus or minus b. So we can separate out, if we have a sum, we can separate out the sums and examine them separately if we need to, if it's easier. Now we can't do multiplication and division quite as easily, because multiplication, you're multiplying, think of how you multiply a polynomial. You have all those terms that are multiplied together. So it's a little more complicated. And division is a lot more complicated because you have a large sum divided by a large sum. So that gets a little more complicated. All right. The big test that I want to talk about today is the nth term test. The nth term test is a nice one, but it's one that we have to be very careful with. So the nth term test, if the sum n equals 1 to infinity of a sub n converges, if this series converges, then the limit as n approaches infinity of a sub n equals 0. If the series converges, the nth term has a limit of 0. And this is really easy to see, so I'm going to say why. We're going to say the sum n equals 1 to infinity of a sub n is L. We're given that. It has some limit. Well, this tells us that the limit as n approaches infinity of the sequence of partial sums is L. That's how we determine the convergence of a series. The sequence of partial sums converges. And this equals the limit as n approaches infinity of one less term plus the nth term. We're just adding one more term here. Well, I can separate these two out. Oops, limit. But if the limit as n approaches infinity of s sub n is L, we're still going, n is approaching infinity. Well, this is still the same limit. So this is L plus the limit as n approaches infinity of a sub n. And we know that the sum is L, this limit is L, so the limit as n approaches infinity of a sub n has to be 0. So our nth term has to approach 0. No, it's easy to, I just wanted to show it's easy to see why this is the case. Where we have to be careful. So if the series converges, then the limit is 0. The converse is not true. So we cannot say if the limit as n approaches infinity of a sub n equals 0, then the series converges. We cannot argue the converse. And we'll get to what we can say in just a second. So we cannot say this. If the limit at a sub n is 0, then the series converges. And I know you learned the counterexample for this. You remember what it is? A harmonic series. What? The sum n equals 1 to infinity of 1 over n diverges. The limit as n approaches infinity of a sub n approaches 0, but this series diverges. That's the counterexample. We're trying to use this converse. The harmonic series diverges. And I'll come back to the harmonic series in just a second, and we'll see why it diverges. It seems like it should converge because it gets the terms get really small. It diverges very, very slowly, but it does diverge. So this is the example you want to remember when you want to, if you decide you want to use this argument. So, oh no, the harmonic series diverges. The contrapositive is true. We're using all these logic terms. So the contrapositive gives us our nth term test for divergence. We can use the nth term test for divergence. So what the contrapositive says is if the limit as n approaches infinity of a sub n is not 0, then the series diverges. The contrapositive and the original statement are logically equivalent. So we change the order and put not in front of everything. We get something that's logically equivalent to our original. So this is equivalent to saying if a sub n converges, then the limit of the terms approaches 0. It's logically equivalent to saying this. So this gives us a test for divergence. And this is usually the first thing you want to look at if you're testing a series for convergence. Look at the limit as n approaches infinity. If that limit is not 0, then the series diverges. And that's an easy test. So that's our main test today. Nth term test for divergence. So let's look at a couple of quick examples. Or I have questions. So any questions on this? And then we'll come back to the harmonic series. If our nth term, n plus 1 over n, does this converge? So first off, what is this? When we put the term in braces like that. Sequence. So for a sequence to converge, all we care about is what? We had a big discussion about this the other day. Bounded monotonic, and really what we're interested in, big picture, the end behavior. All we're interested in is the limit. Does this thing have a limit?
Yeah.
Limit as n approaches infinity of a sub n is 1. So now I'm going to say, does the sum converge? Yeah, 1 doesn't equal 0. Our nth term, the limit as n approaches infinity of a sub n is not 0. So the series diverges. So this sequence converges because the nth term has a limit, but this series does not converge because the nth term does not approach 0 as n approaches infinity. So when you're looking at sequences and series, make sure you make the distinction. Are we talking about sequences? Are we talking about series? because the idea of convergence for a sequence is different than the idea of convergence for a series. Now, if we're talking about the sequence of partial sums, then we're talking about the same thing. All right. I want to know what the difference is between these things. I guess does the colon, is that the correct thing? I'm not sure it is. Yes.
We looked at this with the last problem with the example from the lab thing, where the sequence, each new term being generated. So if we're thinking of A of n, of generating a new term each time, the sequence is just separating it by commas, saying there's no relationship between the terms.
Other than the thing, the rule that generates them. Yeah.
They're not being. There's nothing being done with them.
No.
They're just there.
You're just listing them.
If they converge to anything, that means you can say, well, the nth term is 1. Eventually, it's close enough to 1 that we can say it's 1. It's
right.
It's the new term being generated, because once you start adding things, then if the numbers are getting bigger, they're going to go without bound. If the limit is anything but 0,
right, because
grow without bound.
Right, because you're going to constantly being adding something.
Another number.
Right, another number. So that's how you would go about. Your argument is essentially the proof of the contrapositive that we just said. That if the nth term doesn't approach 0, then it can't converge. Yeah. All right. So I'm going to list 3 things. All right. So what's the difference between these 2 things? So what is this? What is this first one? This is just a series. What about this one?
That's also just a series.
Yeah, that's just a series. We're just indexing with k's instead of n's. How about this one?
That's
What's that? That's a good word. So we're adding up an infinite number of things.
But there's no thing has to be changed.
This is right. A sub k is a constant. So this is just a sub k plus a sub k plus a sub k plus dot dot dot.
So it's a geometric series with a ratio of 1. Right?
Well, it depends on what a sub k is. A sub k could be 1,000.
But the ratio is still 1.
Right, a sub k could be 10. So it is 10 plus 10 plus 10 plus 10 plus 10. So this is just a sum of a constant. So sometimes indices tell us we're adding a bunch of different things together. Sometimes they're kind of tricky and we're not adding a bunch of different things together. We're adding the same things.
But if you just have multiple sigmas out front, you can have multiple.
Right. You could have multiple summations, and then you have to be careful of which one goes with what. Right. All right. Finally, let's see that the harmonic series diverges. So you don't just have to take my word for it.
Are we going to talk about the harmonic series like as a test separately because it is?
We'll compare a lot of things to the harmonic series because we know it diverges.
Alternating harmonic series converges.
What's that?
The alternating harmonic series converges.
Alternating harmonic series converges. So we know that the limit as n approaches infinity of a sub n is 0. But the sum n equals 1 to infinity, I'm going to write out some terms. 1 plus 1/2 plus 1/3 plus 1/4. Well, 1/3 plus 1/4 is greater than 1/2. Plus 1/5, plus 1/6, plus 1/7, plus 1/8. Those four terms are greater than 1/2. Plus, and I could group the next 8 terms together, and they would be greater than 1/2. So what I'm saying is the sum n equals 1 to infinity of 1 over n is greater than 1 plus 1/2 plus 1/2 plus 1/2 plus dot dot dot, which diverges. The sequence of partial sums diverge. So this is why the harmonic series, or a demonstration that the harmonic series diverges.
What if they were all being subtracted?
They're all being subtracted. So so if we had negative 1 over n, it's just, we could just pull that negative sign out front,
Yeah,
and then it's the same problem.
So that it's only if it's alternating that you get the
Right.
special stuff.
And tomorrow when we talk about the integral test, we'll see, we can see another demonstration that has to do with the harmonic series. Okay, questions? All right.
Homework, really? It just is that. I like that. Can you go to oh my god, really? That was like so crazy.
Yeah? Sure. All right, I'm gonna back up really quickly here. Mm-hmm.
Oh my god, Lily.
I didn't hear it. I didn't know what happened.
I touched my back and like everybody ran my back.
It was
Everyone in this
so loud. It was so
You good?
awesome. It was just like